Hello everyone. We are excited to present our CVPR 2026 highlight paper titled LLMind, Bio-Inspired Training-Free Adaptive Visual Representations for Vision Language Models. Even after significant advances in vision language perception, current VLMs still rely on uniform spatial processing, treating all image regions with equal importance. However, in real-world scenes, the critical information is often sparse and distributed across distant regions of the image. Moreover, current VLMs struggle with very large images. Although downsampling reduces computation, it also removes the fine details required for accurate reasoning, causing even advanced foundation models to fail at low resolutions. This raises an important question. Instead of uniformly downsampling the entire image, can we adaptively allocate more pixels to task-relevant regions while suppressing irrelevant ones? As shown here, uniform sampling fails to preserve the details needed for correct reasoning, whereas adaptive sampling retains the critical visual evidence, even under the same pixel budget. This naturally leads us to human vision, which is inherently adaptive, selective, efficient, and task-driven. Humans allocate higher visual fidelity to important regions through cortical magnification, and rapidly shift attention toward informative locations using saccadic eye movements, enabling efficient perception without uniformly processing the entire visual field. This motivates our central research question. Can biologically inspired sampling strategies enable VLMs to achieve higher reasoning efficiency and accuracy than conventional uniform sampling under limited pixel budgets? To answer this question, we introduce LLMind, looking like the mind, a bio-inspired, training-free framework for adaptive visual representation in vision language models operating under strict pixel budgets. At the core of LLMind, there is a bio-inspired adaptive sampling strategy called BASS. Given an input image, we use a Mobius transformation to adaptively warp the image space. A Mobius transformation is a conformal mapping that serves as a mathematical analog of cortical magnification in human vision, magnifying task-relevant regions while smoothly compressing less important areas. The transformation is controlled by a set of learned Mobius coefficients, which determine how the image should be spatially reallocated for the current reasoning task. Next, the warped image is passed through a sampling and interpolation stage, where the available pixel budget is allocated more densely around important visual regions and more sparsely over irrelevant background regions. Finally, an inverse Mobius transformation maps the sampled representation back into the original image space, producing the final sampled image. Now let us take a look at the overall framework. Given an input image, a lightweight MLP network first predicts the Mobius transformation coefficients. These coefficients are then used by BASS to generate the adaptively sampled image. A perceptual reconstruction loss is applied between the original image and the sampled image to preserve visual fidelity. In parallel, a frozen vision language model processes the sampled image along with the input question to generate the predicted answer. The predicted answer is then compared with the ground truth answer to compute a semantic loss, which guides the optimization of the sampling strategy through SPSA-based closed-loop semantic feedback for test time optimization. This entire process is repeated for T iterations, progressively refining the sampling strategy toward more task-relevant visual regions. We extensively evaluate LLMind against uniform and other adaptive sampling baselines across diverse benchmark datasets. For scene-level VQA tasks, LLMind improves the average performance over uniform sampling under the same pixel budget by plus 20% on VQA v2, plus 38% on Seedbench, and plus 37% on A-OKVQA, while for region-guided VQA, it achieves an average gain of 35% over uniform sampling, and even surpasses full-resolution accuracy, using only 1% of the pixels. LLMind is model-agnostic and can be integrated as a computational front-end with any VLM, including black box models. The following video showcases the iterative optimization process of LLMind, using Qwen 2.5 VL on the Seedbench dataset. Notice how the focus progressively shifts toward the task-relevant regions over the iterations, closely mimicking the cortical magnification and saccadic eye movements of human vision. The key contributions of this research are a bio-inspired training-free adaptive sampling framework for efficient VLM perception, a Mobius transformation-based sampling strategy for non-uniform pixel allocation, a model-agnostic closed-loop semantic feedback mechanism for test time alignment, and consistent VQA gains under extreme pixel budget constraints across diverse settings. Our study suggests that a large portion of pixels processed by modern VLMs are often unnecessary for reasoning, as LLMind retains up to 82%, 92%, and 97% of the full resolution performance using only 1%, 3%, and 5% of the pixels respectively. We hope this work encourages future research toward more adaptive, efficient, and biologically inspired visual perception systems. For more information, please visit our project page. See you in Denver.